Stone giants rose toward the clouds without any modern machinery. These great cathedrals of Europe are monuments not just to faith, but to a forgotten age of engineering genius. By the end of our journey, you will possess a complete understanding of the 25 specific innovations that made these impossible structures a reality. We will uncover how medieval builders defied gravity with stone arms that leap through the air and how they turned walls into luminous curtains of colored light. What does it truly take to build a world that lasts for 1,000 years? A cathedral's true strength is hidden deep beneath your feet. Before those breathtaking walls could even be dreamed of, medieval builders confronted their first and most critical challenge, the ground itself. They had to answer a seemingly impossible question. How do you anchor a mountain of stone into soft, unstable earth? Their brilliant solution was the deep trench foundation. Imagine digging massive trenches far wider than the future walls, and then filling them layer by layer with a deliberate mixture of rammed earth and rubble. This created an artificial bedrock, a wide foot that spread the building's colossal weight over a much larger area, preventing it from simply sinking into the ground. At Chartres Cathedral, they took this concept to its ultimate conclusion. Builders did not stop digging until their shovels struck the actual, unyielding bedrock beneath the soil. They essentially created a stone raft, a single, solid platform upon which the entire cathedral would forever float. This fundamental mastery of load distribution was a leap of intuition that we now call soil mechanics. But how could they possibly know how deep to dig without any of our modern testing equipment? Theirs was a knowledge written in the landscape, learned through generations of painful trial and error. They read the land, understood its water, and learned from the failures of those who came before. This invisible, subterranean engineering was the silent, non-negotiable contract with the future. It was the promise that the walls about to rise would stand for 1,000 years. But that deep foundation could only support so much. With a stable base secured, medieval engineers now faced a new and even more dramatic problem in the sky. The immense weight of the stone roof created a powerful outward thrust, pushing against the walls and threatening to make the entire structure buckle and collapse. The solution was a stroke of architectural genius so daring it seemed to defy logic itself. They built supports on the outside. The Flying Buttress was born, a stone arm that leaps through the air from a free-standing pier to brace the cathedral's high wall. This external skeleton completely changed the rules of construction. By channeling the roof's destructive thrust outwards and then down into the ground through these external piers, the walls themselves were suddenly liberated. They no longer had to be thick, heavy barriers whose only job was to hold up the roof. Now they could become something entirely new, something previously unimaginable. They could become vast, delicate curtains of colored light. At the Cathedral of Notre Dame in Paris, you can see this system in its most elegant form. Those graceful, arched stone arms are not just decorative, they are the very reason the building stands, a brilliant piece of structural gymnastics that turned solid masonry into a seemingly weightless frame. This single innovation redefined what a building could be, transforming the dark, fortress-like Romanesque church into the soaring, luminous space we recognize as Gothic. It was this skeletal strength that made the next impossible dream a reality, the dream of capturing sunlight and turning it into a divine story. Look up. Inside these vast stone chambers, the ceiling itself is a testament to a hidden revolution in engineering. Earlier churches used massive, tunnel-like barrel vaults, which were heavy, dark, and required thick, unbroken walls for support. The Gothic builders shattered this tradition with the invention of the ribbed vault. This was not a solid stone shell, but a brilliant skeletal framework. Picture a series of arched stone ribs like the bones of a great stone beast crossing high overhead. The spaces between these ribs, called the webbing, were then filled with much thinner, lighter stone panels. This single change was transformative. The ribs acted like a superstructure, channeling the entire weight of the roof down through their curves and concentrating it onto a few specific, powerful points. This is the crucial internal partner to the Flying Buttress. Those external arms could only do their job because the ribbed vault told the roof's weight exactly where to go, directing the thrust outward to be gracefully caught and neutralized. This system was also a marvel of prefabrication. The complex stone ribs were often pre-carved in the mason's yard, shaped with incredible precision before being hoisted into place. This allowed for not just stronger construction, but for breathtaking artistic expression. In the nave of Amiens Cathedral, you can see this genius fully realized, with a complex geometric lattice of ribs creating a canopy that seems both impossibly light and eternally strong. It was essentially the medieval version of a modern space frame, a principle we see in everything from airplane wings to grand stadium roofs, proving that true strength often lies not in a solid mass, but in a perfectly designed skeleton. This newfound ability to build lighter and stronger ceilings unlocked the next great ambition, a drive that would push medieval engineering to its absolute limit, the race for height. That skeletal framework of ribs created a new kind of pressure, a vertical one. To truly race towards the heavens, builders needed to reshape the very curve of stone itself. The rounded Romanesque arch, inherited from ancient Rome, had a fundamental weakness. Its perfect semicircle pushed weight outward with a powerful, unyielding lateral thrust. This force demanded thick, fortress-like walls to contain it, limiting both height and light. The Gothic solution was a geometric revolution, the pointed arch. This was not merely a stylistic whim, it was a profound recalibration of physics. By rising to a point, the arch channels its load more directly downward into the supporting pillars below. This clever geometry dramatically reduced the outward push, liberating the walls from their burdensome role as sheer buttresses. Suddenly, those walls could be pierced with vast openings, and the entire structure could climb to unprecedented heights. At Reims Cathedral, this principle was pushed to its limits. The pointed arches create a breathtaking sense of verticality, drawing the eye irresistibly upward, making the stone itself seem to defy its own weight. This single form became the fundamental DNA of the Gothic style, its acute angle dictating the proportions of vaults, windows, and portals. It was the essential partner to the ribbed vault and the Flying Buttress, a trio of innovations that worked in perfect harmony. The arch directed weight down, the vault channeled it out, and the buttress gracefully caught it. This was not just building, it was a form of architectural alchemy, turning the crushing force of gravity into an expression of weightless aspiration. And once they had mastered this new geometry of stone, they faced their next great challenge: how to fill those newly liberated walls with something even more ethereal than light itself. These soaring stone ribs and pointed arches created a new kind of pressure, a force that needed a perfect path to the earth. But how do you guide that immense, concentrated weight from a complex web of vaults down through the body of the building without creating visual chaos? The answer lies in a masterstroke of integrated design, the Compound Pier. These were not the simple, round columns of antiquity. They were sophisticated clusters of stone, a bundle of slender shafts attached to a central core. Each one of these small shafts was meticulously aligned to meet a specific rib from the vaults high above, creating a continuous visual line from the floor all the way to the ceiling. This was far more than a decorative flourish. It was a brilliant structural diagram carved in stone. Each small column was a dedicated load-bearing member, carrying the weight from its assigned rib in a perfectly efficient, direct path to the foundation. At Canterbury Cathedral, you can see this principle in its most elegant form. The compound piers rise like stone trees, their bundled branches reaching up to seamlessly connect with the intricate vaulting overhead. This intelligent design provided immense strength without the overwhelming visual bulk of a single, massive column. It demonstrated a profound understanding of how to break down and manage complex forces, channeling the chaotic weight of the roof into an orderly, manageable procession down to the ground. This was structural honesty made beautiful, a perfect marriage of engineering necessity and aesthetic vision that made the entire interior space feel like a single, unified ascent. And once this elegant skeletal system was complete, from the compound piers to the ribbed vaults, builders confronted their next great challenge: how to encase this stone framework in walls that were not really walls at all, but something closer to solidified light. Those walls, now freed from their load-bearing duties, underwent a transformation as radical as it was beautiful. They became vast, shimmering curtains of colored light, and this miracle was made possible by a hidden engineering marvel, the art of tracery. Look at the windows of Sainte-Chapelle in Paris, where the walls seem to dissolve into a kaleidoscope of sapphire and ruby. This is not an illusion, it is structural genius. The immense openings for these windows are not empty voids. They are filled with a delicate-looking but incredibly strong framework of carved stone. This is tracery, a skeleton of stone designed specifically to support the weight of the glass and resist the relentless push of the wind. Initially, builders used a method called plate tracery. Imagine cutting simple, circular or almond-shaped holes into a solid stone wall and then filling them with glass. It was a start, but the stone still dominated. The true breakthrough came with bar tracery. This was a complete reversal of the idea. Instead of cutting holes in a wall, the masons built the window from a network of slender stone bars, weaving them together into intricate geometric patterns. These patterns, flowing and flamboyant, were far from random. Every curve, every intersection was a carefully calculated distribution of stone, a perfect balance of beauty and structural stability. This intricate stone lacework allowed the walls to become primarily transparent, a concept that would have been unthinkable just a generation before. But such a delicate-looking facade could only stand because of its perfect partnership with the robust external skeleton of flying buttresses. The buttresses dealt with the massive thrust from the roof, while the tracery managed the localized forces on the wall itself. This holistic design, where every element worked in concert, turned architecture inside out, transforming heavy, earthly masonry into a vessel for capturing and coloring light itself. And to hold that luminous vision in place, they needed to invent a new kind of material, one that was both strong as stone and transparent as air. Each perfect stone arch we see today was once a promise held up by wood. To turn their drawings on parchment into curves in the sky, medieval builders depended on a temporary but absolutely essential structure, the centering. This was a complex wooden framework, a custom-built skeleton erected to support the precisely cut stones of an arch or vault until the mortar between them had fully set. Designing these centerings was an engineering discipline all its own. The master carpenter had to calculate not just the final shape, but the immense weight of the wet masonry and the pressure it would exert on his timber creation. This demanded a profound understanding of wood, its grain, its strength, and the intricate joinery that could lock it all together without a single metal nail. For a project as vast as the Cologne Cathedral, the Carpenters' Guild operated as a parallel power to the stonemasons, their skill with the axe and adze every bit as critical as the mason's mastery of the chisel. The centering they built had to be perfectly, unerringly shaped, a robust timber mold that would hold its form for months on end, often through harsh weather, without sagging or shifting even a fraction of an inch. This entire temporary infrastructure represented a colossal investment of time, material, and artisan skill, a hidden cost embedded in every graceful stone curve that now seems to float so effortlessly. The most dramatic moment in the entire process was the striking of the centering. After the mortar had cured, workers would carefully knock away the wooden supports. It was a tense, silent prelude, a true test of the mason's geometric precision and the soundness of the design itself. If the stones settled into a perfect, stable arch, it was a triumph. If they shifted or cracked, it was a catastrophic failure. This risky, patient process was the invisible birth of every vault and doorway, a temporary wooden womb that gave way to a permanent stone skeleton. And once that skeleton was secure, builders faced a new puzzle: how to protect their colossal investment from a silent, creeping enemy that could bring it all down from within. Every graceful curve and soaring arch we admire today began not on the scaffold, but on the workshop floor. The secret to this impossible precision was a master science known as stereotomy, the art of cutting solid stone into complex, interlocking shapes. Armed with nothing more than chisels, mallets, and squares, medieval masons performed a kind of geometric magic. They transformed rough blocks into intricate puzzle pieces, each one destined for a single, unique location in the grand design. The key to this consistency was the use of templates, often carved from wood or thin metal. These patterns, derived from detailed drawings in master model books, guided the mason's hand as they carved the critical stones, the voussoirs for arches and the ribs for vaults. Imagine the workshop at Chartres Cathedral, a place humming with focused activity. Here, skilled artisans interpreted two-dimensional diagrams, translating lines on parchment into perfect three-dimensional stone components. This was a form of prefabrication centuries before the term existed. Each stone was numbered and finished in the yard, then shipped to the construction site ready for assembly. The entire cathedral was, in effect, a massive, pre-engineered stone kit. Its success depended entirely on the meticulous work of countless anonymous hands. If a single arch stone was cut even slightly wrong, the entire structure could fail when the temporary wooden supports were removed. This relentless dedication to accuracy is why the complex patterns of ribs overhead locked together so seamlessly, a silent testament to the nameless artisans whose genius was measured in millimeters and whose legacy is a world built to last 1,000 years. Yet for all their geometric genius, stone and wood could only solve half the engineering puzzle. Stone is magnificent at resisting crushing forces, but it is brittle and weak when pulled or stretched. This is the fundamental difference between compressive strength and tensile strength, a challenge the Gothic builders met with a hidden innovation. They began weaving metal into the very fabric of their cathedrals. Long before the age of steel and reinforced concrete, these master builders understood the unique properties of iron. They forged robust iron bars known as tie rods and strategically threaded them through arches and across spaces to act like permanent, unyielding belts, counteracting the persistent outward thrust that threatened to push walls apart. They also crafted sturdy iron cramps, which are essentially large metal staples, to lock adjacent stones together, creating a unified, monolithic structure out of countless individual blocks. Nowhere was this metallic skeleton more crucial than at Beauvais Cathedral, a structure that reached for the heavens with an ambition that bordered on defiance. To achieve its breathtaking, record-breaking height, the builders at Beauvais integrated iron reinforcement directly within the masonry itself. This was an early and brilliant form of composite construction, a pragmatic marriage of materials that used stone to handle the immense downward weight and iron to manage the destructive pulling and stretching forces. This hidden network of metal was their secret weapon against gravity's relentless pull. Of course, this innovation was not without its long-term consequences. Centuries later, moisture would sometimes cause these iron elements to rust and expand, a process that could fracture the very stone they were meant to protect. Yet this occasional later issue does not diminish the brilliance of the original solution. It simply highlights that these builders were practical problem solvers, using the best technology available to them to push the boundaries of the possible. They were not purists, they were pioneers, willing to combine the ancient strength of stone with the resilient power of metal to create something entirely new. This hidden ironwork is a quiet testament to their flexible, resourceful genius, a crucial layer of strength woven into the heart of the stone. High above the intricate stone vaults, in the shadowy space between the ceiling and the sky, lies another world of engineering entirely. This is the realm of the master carpenter, a hidden forest of timber built to shield the stone skeleton below. These were not mere rafters, but complex truss systems, engineered to span vast distances and withstand centuries of wind and weather. Their design was a brilliant balancing act, using triangular forms to create structures of immense strength and surprising lightness. The ultimate expression of this wooden art was the hammerbeam roof. Imagine a series of short, powerful horizontal beams projecting inward from the walls, each one cantilevering out to support a network of arched braces and vertical posts. This ingenious arrangement transferred the roof's weight back to the walls, allowing craftsmen to span a breathtakingly wide space without any central columns to interrupt the view below. In Westminster Hall, the sheer scale of the hammerbeam roof is overwhelming, a testament to carpentry that feels as permanent and powerful as the stone it protects. The carpenters who conceived these structures possessed a deep, almost intuitive knowledge of their material. They knew how wood would shrink, swell, and shift over the seasons, and they designed their joints not as rigid locks, but as sophisticated connections that could accommodate this natural movement without failing. Each mortise and tenon, each scarf joint and lap, was a calculated decision in a long-term dialogue with the forces of nature. These vast wooden frameworks were the cathedral's first and most vital line of defense, a durable shield that kept rain and snow from seeping into the delicate stone vaults. They represent a parallel branch of medieval genius, proving that the quest for height and light was supported by an equal mastery of the forest, and protecting this entire wooden world from its oldest enemy would require a final, fiery innovation. The final, most audacious gesture in this stone symphony was the spire, a needle of masonry aimed directly at the heavens. At Strasbourg Cathedral, the single soaring spire stands as a breathtaking testament to an ambition that borders on the impossible. Constructing such a slender stone needle required an engineering foundation of absolute stability. The massive towers below had to be perfectly squared and leveled, providing an unyielding platform for this delicate final act. Every stone course was laid with meticulous precision, checked and rechecked with weighted plumb lines to ensure the entire structure remained perfectly vertical against the relentless push of the wind. Inside the tower, narrow spiral staircases coiled upwards, the only access for builders hauling materials into the sky. Sometimes, a great central mast of timber was erected first, acting as a giant guide and a temporary support for the emerging stone shell. To bind the entire structure together against lateral forces, masons often drilled holes and connected adjacent stones with dowels of wood or metal, turning the spire into a single, unified monolith capable of resisting the constant threat of wind shear. The completion of a spire was more than just an architectural milestone. It was the crowning achievement of a campaign that might have spanned generations, a brilliant and visible symbol of a community's collective faith and prosperity. It represented the absolute outer limit of what was physically possible with cut stone, a final, fearless declaration of mastery over the vertical dimension. But to place those final stones at such a dizzying height, medieval engineers first had to conquer the air itself, relying on machines of breathtaking ingenuity to lift their dreams from the ground. That stone spire piercing the sky was lifted there not by magic, but by the steady, rhythmic footsteps of men inside a giant wooden wheel. High above the bustling construction site, housed within the rising towers of the cathedral itself, was the medieval crane, a human-powered machine of breathtaking ingenuity. The most iconic of these was the Great Treadmill Crane, a massive wooden wheel that functioned like a squirrel cage for people. Laborers would step inside, walking steadily forward to turn the entire wheel, which then wound a heavy rope around a central axle, hoisting multi-ton stones from the ground with painstaking control. A surviving sketch from the notebook of a master builder named Villard de Honnecourt reveals the sophistication of this design, showing a sturdy wooden frame and a complex system of pulleys that multiplied the workers' strength. This mechanical advantage was the true miracle, allowing a small team of men to lift weights that would have been impossible through sheer muscle alone. Operating this machine required immense coordination and courage. The men inside the wheel had to walk in perfect unison, their collective weight and momentum providing the smooth, consistent power needed to raise a precisely carved block of stone hundreds of feet into the air, where other workers, perched on narrow scaffolding, would guide it into its final, perfect position. This was the critical link between the mason's drawing and the finished arch, the essential muscle that translated geometric theory into physical reality. Without this relentless, grinding mechanical power, the flying buttresses, the ribbed vaults, and the soaring spires would have remained nothing more than dreams on parchment. But the genius of these spaces extended far beyond what the eye could see. Step inside a completed cathedral and close your eyes for a moment. The very air itself seems to vibrate with a life of its own, a deep, resonant hum that lingers long after a single note has been sung. This was not an accidental quality. It was a carefully, if intuitively, crafted auditory environment, an acoustic engineering feat as deliberate as any stone arch. Medieval builders understood that sound was a physical force to be shaped and guided. The vast, uninterrupted volumes, the hard, polished stone surfaces, and the specific curves of the vaults overhead were all chosen to create a long, luxurious reverberation time. A single chord from the choir would not simply stop, it would swell and echo, washing over the congregation in overlapping waves of harmony. This sonic characteristic was perfectly suited to the complex, interweaving lines of Gregorian chant and early polyphonic music, transforming a human performance into an ethereal, all-encompassing experience. The space itself became a colossal musical instrument. Builders learned through practice that certain proportions and parabolic curves could act as natural amplifiers, projecting the sound of the liturgy from the choir screen clearly down the entire length of the nave, ensuring that even those standing at the very back felt immersed in the sacred ritual. This creation of a sacred soundscape reveals a design philosophy that was breathtakingly holistic. It was not enough for the building to be strong or beautiful. It had to engage every sense, to elevate the spirit through a symphony of stone and air. This attention to the intangible demonstrates that their engineering addressed the complete human experience, crafting an environment where sight, sound, and spirit fused into a single, transcendent moment. And to achieve this perfect resonance, they first had to master the art of shaping and moving the very stone that created it, a process that began with a simple, brilliant tool. A cathedral's battle against time was often a silent war waged against water itself. While the soaring stonework captured all the glory, the building's true longevity depended on a hidden network designed for a single, critical purpose: to keep the structure dry. This was the unsung engineering of water management. Far from being simple decorations, the lead gutters that traced the roof lines and the fantastical gargoyles jutting from the parapets were essential components of a sophisticated weatherproofing system. Each gargoyle, with its grotesque form and purposefully elongated spout, acted as a precision waterspout, projecting rainwater clear of the delicate masonry face below. This prevented a relentless, dripping erosion that could, over centuries, dissolve the very carvings and weaken the mortar joints, but deflecting water from the walls was only half the solution. The foundation, that carefully laid stone raft, was equally vulnerable to saturation. Builders countered this with complex networks of underground drains and soakaways, channels and pits filled with rubble that captured groundwater and surface runoff, redirecting it safely away from the building's base. At Milan Cathedral, the roof itself is a veritable landscape of pinnacles and spires, each one not just a decorative element but a strategic component in a grand design to shed water swiftly and efficiently across a vast surface. This meticulous attention to hydrology was a defensive measure against the slow, destructive forces of damp and frost. When water seeps into stone and freezes, it expands with incredible force, a process called frost weathering that can crack the hardest granite from within. By mastering the flow of water across and around their structures, these builders were practicing a form of preventative medicine for their stone creations. This often overlooked infrastructure reveals a profound understanding of their environment, proving that their genius extended beyond defying gravity to controlling the very elements that sought to reclaim their work. It was this holistic vision, protecting the building from the top of its spire to the bottom of its foundation, that allowed these stone giants to endure through 1,000 winters. A cathedral's most powerful statement was often made at its front door. The monumental Western Facade, that vast stone screen facing the city, was far more than a decorative mask. It was a carefully engineered gateway, a structural puzzle of immense scale and symbolic weight. At Notre Dame de Paris, the iconic twin towers rise from a wall that appears perfectly flat, yet this is an illusion of masterful composition. The entire structure is a lesson in balanced forces. To prevent this great stone curtain from buckling under its own weight and the relentless push of the wind, builders employed a principle of clever massing. They flanked the central section with sturdy, projecting buttress towers, anchoring the ends and providing deep lateral support, but the real genius was hidden within the wall itself. Internal galleries running horizontally through the body of the facade acted as stiffening diaphragms. These are not merely passageways, they function like the horizontal braces in a modern skyscraper, tying the entire structure together and preventing it from swaying or leaning. This internal skeleton gave the wall the rigidity it needed to stand tall and support the immense load of future towers. The famous rose window is not just a burst of colored light. It is a calculated void, its placement and surrounding stonework meticulously designed to distribute weight around its circumference. Even the deep portals and the armies of sculpted saints are part of this structural scheme. Each recessed doorway and carved niche adds visual and physical depth, breaking up the flat surface and creating a self-buttressing form that contributes to the whole's stability. The westwork was therefore a holistic engineering triumph. It had to be a grand, stable screen capable of resisting immense forces, a symbolic face for the urban landscape, and a durable platform for towers that would reach for the clouds. This was the application of structural principles to the ultimate challenge of first impressions, creating a monumental gateway that was, in every sense, as strong as it was beautiful. Behind the high altar, the cathedral unfolds into a graceful, curving corridor of stone and light. This is the ambulatory, a brilliant solution to a problem of both faith and physics. Medieval architects needed to design an east end that could accommodate a constant stream of pilgrims, all hoping to glimpse the sacred relics housed behind the main altar without disrupting the ongoing liturgy. Their answer was a structural masterstroke, a processional pathway that wrapped itself around the sanctuary like a stone embrace. This semi-circular hallway, the ambulatory, allowed for a continuous, one-way flow of human traffic. But this elegant solution created an engineering puzzle of its own. The curved outer wall of this hallway needed to be strong enough to support a roof, yet it was also pierced by a series of small, private chapels that radiated outwards like petals on a flower. How could they build these multiple chapels without creating a chaotic mess of conflicting thrusts and unstable walls? The genius lay in a system of concealed buttressing. The outward push from the semi-domed vault of the main apse, the focal point of the entire east end, was silently caught and channeled downward by a hidden ring of masonry supports built into the spaces between the radiating chapels. You can see this perfect harmony of form and function at the Abbey Church of St. Denis, widely considered the very cradle of the Gothic style. Here, the ambulatory and its chapels are not just added on, they are fully integrated into the building's skeletal logic. The vaults of the hallway and the chapels intersect in a complex geometric dance, each rib and arch carefully calculated to direct its load to a specific, sturdy point. This required a revolutionary understanding of how to manage forces across a non-rectangular, curving plan, a true leap in spatial reasoning. It was architecture in the service of movement and ritual, creating a space that was at once a serene, unhurried procession for the faithful and a stunning testament to the medieval mind's ability to weave together complex structural demands into a single, seamless, and breathtakingly beautiful whole. Beneath the soaring vaults of Chartres Cathedral, your feet trace a path laid 1,000 years ago. The great labyrinth set into the stone floor is a journey in miniature, a winding spiritual quest for those who walk its sacred geometry. Yet these precise, concentric circles and complex turns may hold a secret purpose far more grounded than the heavens. This intricate floor pattern, centered with absolute perfection in the nave, could have been the master builder's ultimate surveying tool. Picture the vast, unfinished interior, a chaotic forest of scaffolding and rising walls. How could a handful of overseers ensure that every new pier was erected perfectly plumb and true, aligned with the grand axis of the entire design? The labyrinth offered a permanent, immutable answer. By sighting along its key lines, builders could establish perfect right angles and verify the alignment of distant columns across the cavernous space. It was a giant, fixed diagram etched directly into the foundation of the building itself, a constant reference that ensured the work of generations remained geometrically harmonious. This hidden function reveals the profound unity of medieval thought, where the sacred and the scientific were not separate realms. The same mathematical principles that expressed divine order were also the most practical tools for construction. The labyrinth fused spiritual symbolism with applied engineering, turning a prayerful path into a master blueprint for stability and precision. It reminds us that in these cathedrals, even the floor beneath your feet is part of the structural story, a silent, steadfast guide that helped keep a stone giant standing straight for 1,000 years. That master diagram etched into the floor was the final expression of a plan laid out long before the first foundation stone was ever set. Every cathedral began as an idea drawn in the earth itself. On a carefully cleared patch of ground, the master mason and his team would perform a kind of sacred geometry, using nothing more than ropes, wooden stakes, and a profound knowledge of mathematical principles. This was the critical act of setting out. The moment a dream was given its physical dimensions, they employed methods with ancient names, ad quadratum and ad triangulum, which simply meant building the plan from the perfect, timeless shapes of the square and the triangle. A square could define the basic module of the nave, while rotating that square or inscribing triangles within it would generate the proportions for the transepts and the choir. This was not guesswork, it was a rigorous application of universal order. The master mason's tools were humble yet powerful, the compass for drawing perfect circles and arcs, and the straight edge for defining true lines. With these, he scratched and pegged a full-scale blueprint directly onto the construction site. The accuracy of this initial layout was absolutely paramount, because a tiny error of a single degree at ground level would be magnified into a catastrophic misalignment hundreds of feet in the air. This is why so many cathedrals, from Amiens to Canterbury, share a familiar, harmonious feel. They were all born from the same shared body of geometric knowledge, a secret language of proportion passed from master to apprentice. This invisible foundation of ropes and stakes was the true intellectual bedrock of the entire project. It proves that these soaring monuments to faith were also monuments to reason, born from meticulous premeditation and a deep, abiding belief that the universe itself was built upon a mathematical order, an order they would now express in the perfect ribs of their stone vaults. A perfect circle of stone and light hangs suspended in the western wall, a geometric paradox that seems to defy the very logic of masonry. The great rose window is far more than a beautiful picture made of glass. It is a structural wheel engineered to turn a wall's greatest weakness into its most brilliant strength. Creating such a vast circular opening in a load-bearing wall was an invitation for collapse, as the weight from above would naturally seek to crush the void. The Gothic solution was to treat the entire assembly not as a whole, but as a rigid, self-supporting stone machine. The intricate tracery inside the window acts exactly like the spokes of a mighty wheel, each slender bar of stone channeling the immense compressive forces evenly outward to the solid masonry that encircles it. This transforms a point of vulnerability into a ring of incredible stability. At Notre Dame de Paris, the West Rose is a masterclass in this principle. Its complex, radiating pattern of stone and glass is a carefully calculated distribution of weight, a web of interlocking segments that lock the entire circle into a single, unified entity. This stone wheel was then further braced by the deep, arched layers of the surrounding portal and the hidden buttressing within the facade itself. Crafting each curved stone for the circular frame demanded the absolute peak of stereotomic skill, with masons carving complex three-dimensional puzzles that had to fit together with flawless precision. This is the ultimate expression of the Gothic genius, using geometry not to simply decorate a wall, but to reinvent its very nature, making it simultaneously more open to light and more resilient to force. It stands as a breathtaking declaration that true strength is not found in solid mass, but in perfect, beautiful form. The stone itself was a carefully chosen ally in this great endeavor. Medieval builders were pragmatic geologists long before the science had a name, possessing a deep, intuitive understanding that not all stone was created equal. They selected different types for specific structural and aesthetic purposes, treating each block according to its unique strengths and weaknesses. For the foundation and the external facing, where the building met the damp earth and the harsh weather, they chose a hard, durable limestone, a stone capable of resisting crushing weight and centuries of erosion. But step inside and you would find a different material altogether. For the intricate interior sculpture, the delicate foliage, and the expressive faces of saints, they reserved a softer, more easily carved stone. This selective use was a masterstroke of logistics and artistry. At Canterbury Cathedral, this principle reached across national borders. The builders there imported a specific type of limestone from Caen, in France, prized for its fine-grained, almost buttery quality that allowed carvers to achieve a level of detail impossible with the local, coarser stone. This was not an extravagance, it was a calculated decision to optimize the final result. Their material science extended deep into the structural skeleton. In areas of immense compression, like the bottom courses of a massive pier, they would use the densest, strongest stone available. Higher up, in the complex web of the vaults where every ounce of weight mattered, they might switch to a lighter, more porous variety. This careful sorting reduced the overall dead load on the structure and made the daunting task of hoisting stones into the sky slightly less Herculean. This empirical but highly effective approach to materials maximized the potential of every resource. It created a building that was not a monolith, but a composite, each part perfectly suited to its role in the grand design, a resilient partnership between human intention and the ancient character of the earth. A cathedral does not simply stand against the wind, it dances with it. These slender stone giants were engineered not as rigid monoliths, but as unified, breathing structures designed to absorb the relentless push of the storm. The secret to their resilience lies in a concept we now call structural dynamics, an intuitive mastery of how lateral forces move through a building. Every element, from the deepest foundation to the highest spire, worked in concert. The interconnected network of ribbed vaults, flying buttresses, and robust roof trusses acted like a rigid diaphragm, tying the entire stone skeleton together and preventing it from racking or twisting out of shape. This holistic rigidity was the first line of defense, but the builders also understood the need for controlled flexibility. The tallest spires were not built to be utterly stiff. They were designed with a slight, intentional give, allowing them to sway gently in a powerful gale, dissipating the wind's energy without developing catastrophic cracks. Look closely at the top of a flying buttress, and you will often see a stone pinnacle looking like an elegant stone candle. This was far more than a decorative flourish. That pinnacle acted as a permanent counterweight, its mass pressing down on the buttress pier to stabilize it against the overturning force of the wind trying to push it over. The entire cathedral functioned as a single, tuned organism, a complex system for channeling and neutralizing energy. This pre-scientific grasp of physics, learned through observation and passed down through generations, is why these seemingly fragile buildings have weathered 1,000 years of gales. Their hidden flexibility is the final, brilliant layer of the engineering miracle, a deep collaboration with the forces of nature that ensured these stone prayers would never fall. This repeating rhythm of arches is the very pulse of the cathedral's interior space. Look down the length of the nave, and you will see a steady procession of these great openings, a structure known as the arcade. This is far more than a beautiful row of arches. It is the fundamental backbone of the entire design. Each arch in this series acts as a critical transfer point, a gateway that channels the immense weight from the high nave walls directly down onto the robust shoulders of the compound piers. The proportions of these arches were everything. A tall, narrow arch naturally directs its force more vertically, while a wider, shallower arch pushes outward with greater lateral thrust. The genius of the Gothic pointed arch was its flexibility. By adjusting the steepness of the point, builders could fine-tune this balance, creating a structure that was both breathtakingly tall and inherently stable. At Bourges Cathedral, the arcade reaches a staggering height, a bold experiment in verticality that could only stand because of this precise geometric calibration. This entire repeating module was a masterpiece of integrated engineering. The arcade's success ensured that the crushing loads from the vaults and the roof high above were gathered, organized, and sent on a deliberate, orderly path down to the earth. It was the indispensable link in the great chain of structural logic, a silent, rhythmic procession of strength that made the miracle of the open, luminous nave possible. High up in the cathedral's wall, nestled between the grand arcade and the luminous clerestory, lies a quiet gallery that is easily overlooked. This is the Triforium, a passageway that most visitors never walk, yet it played a silent, crucial role in the building's survival. Far from being a simple decorative band, this middle level was a masterclass in integrated design. It often served as a hidden highway within the wall itself, a narrow corridor that allowed workers to access remote areas for inspection and repairs, a practical feature in a structure built to last for centuries. But its true genius was structural. The Triforium acted as a continuous horizontal brace, a stiffening belt that tied the tall, vulnerable nave walls together. By connecting the vertical supports, this gallery helped distribute the complex loads from the vaults and roof, preventing the walls from bowing outward or twisting under stress. In some designs, like those at Canterbury, the Triforium provided access to the very heart of the masonry, where builders could monitor the condition of hidden iron cramps and internal buttressing. This was a space where the building's secret health could be checked. The Triforium's placement was no accident. It added crucial depth to the wall section, turning a flat, potentially weak plane into a deep, rigid box girder capable of resisting immense forces. This elegant integration reveals a foundational principle of Gothic engineering, that every single part, even the spaces we barely notice, was engineered to serve a dual purpose. Nothing was merely for show, and no space was ever truly wasted. It was this holistic vision of strength, where beauty and function were woven from the same stone, that prepared these structures for their final, most vulnerable test, the slow, relentless passage of time itself. Every single stone in the cathedral wall was a carefully chosen partner in a grand, interlocking dance. This was the art of masonry bonding, a meticulous system ensuring that thousands of individual blocks would behave as one solid mass. The master masons achieved this not through magic, but through a simple, brilliant pattern of staggering the vertical joints between each horizontal course. By ensuring that the seam between two stones in one row was always covered by the solid center of the stone above, they eliminated any continuous line of weakness running up through the wall. This created a grid of immense strength, distributing stress evenly across the entire surface. For even greater unity, they would occasionally employ through stones long blocks that spanned the entire thickness of the wall, effectively stitching the inner and outer faces together like a permanent stone staple. But the true unsung hero of this monolithic bond was the mortar itself. They used a specially formulated lime mortar, a material that did not simply dry, but underwent a slow, chemical curing process that could last for years. This mortar remained slightly flexible, allowing the entire structure to breathe and shift minutely over the centuries without cracking. It was this humble matrix of lime and sand that truly fused the disparate stones into a single, resilient entity. The longevity we witness today is the direct result of this microscopic attention to detail, where the placement of every block was an act of foresight. It was a silent collaboration across generations, a promise that each anonymous artisan's precise work would contribute to a strength far greater than the sum of its parts. Yet all these physical marvels, from the flying buttresses to the ribbed vaults, were governed by a single, unifying principle. The final and perhaps greatest engineering feat was not made of stone or iron, but of pure thought. Underpinning every physical choice was a profound belief in sacred geometry, a conviction that the universe itself was built upon perfect mathematical ratios. The master masons did not merely build a church, they constructed a model of divine order, using compass and straightedge to lay out the cathedral's plan according to biblical numbers and the timeless forms of Platonic solids. The entire cross-section of the nave might be based on a simple equilateral triangle, a direct and powerful symbol of the Holy Trinity. The floor plan often grew from the square and its diagonal, the square root of 2, a ratio of dynamic harmony. This was far more than mystical superstition. These perfect proportions consistently resulted in forms that were inherently stable and structurally sound. The triangle's natural rigidity translated into a resilient building frame, while the harmonious ratios distributed weight and stress in the most efficient way possible. Their belief that mathematical truth was a path to divine truth drove an obsessive pursuit of precision in every measurement. This philosophical framework was the invisible engine behind all the other 24 feats. It was the conviction that by building in alignment with cosmic order, they were not just creating a shelter, but a resonant spiritual instrument, a house for God that was also the ultimate testament to the soaring power of the human intellect. That silent contract with the earth, sealed in the deep trench foundation, grew into a stone symphony that still resonates today. From the hidden geometry of their floor plans to the wind-defying dance of their spires, these cathedrals stand as a collective triumph of human ingenuity over every material limitation. We have journeyed together through 25 specific engineering feats, uncovering the hidden logic in the flying buttress, the clever skeletal strength of the ribbed vault, and the quiet, relentless power of the medieval treadmill crane. These were never acts of blind faith, but of profound, hard-won knowledge. They were the result of relentless experimentation and a deep well of skill, carefully passed from master to apprentice across generations. The true legacy of those anonymous builders is not just in the stone that has weathered 1,000 years, but in the very principles of structural engineering they helped to pioneer, concepts that still shape our skylines today. So let these stone giants inspire you to look closer at the built world around you. See the hidden engineering in the bridge you cross, the subtle physics in the dome above a train station. And if this journey into the mind of the medieval mason has illuminated the past for you, consider joining us as we continue to explore the untold secrets of history. A cathedral's true blueprint was written not on parchment, but in the rhythm of daily life. Surrounding the rising stone skeleton lay a temporary, bustling city, a living workshop dedicated to a single, monumental purpose. This was a logistical ballet on an epic scale, where the constant rumble of carts marked the arrival of stone from quarries miles away. Each block represented a triumph of transport, hauled over rutted tracks by oxen or floated along rivers on barges, a supply chain that had to flow without interruption for decades. And as the walls climbed skyward, a second forest grew around them, a labyrinth of wooden scaffolding that enveloped the structure, providing pathways for workers hundreds of feet in the air. At the heart of this organized chaos stood the lodge, the master mason's command center. Here, precious templates and detailed drawings were guarded like state secrets, and the master himself directed a small army of specialized artisans. This was not a random crowd of laborers, but a highly structured community. Master masons, journeymen, and apprentices worked alongside carpenters, blacksmith sharpening tools, and glassmakers preparing their radiant panels, all living in a purpose-built settlement near the site. Theirs was a society bound by skill and a shared, lifelong goal. Funding this decades-long endeavor required a different kind of architecture, one of finance and faith. The immense costs were shouldered by the church, yes, but also by wealthy guilds seeking prestige and through the small, faithful donations of thousands of ordinary people, each contributing to a legacy they knew they might never see finished. This human ecosystem, with its complex hierarchies and sustained cooperation, was the final, indispensable engineering feat. It was the living engine that transformed 25 brilliant innovations from abstract ideas into everlasting stone, a breathtaking reminder that the greatest structures are always, ultimately, built by communities.